Hi, so in this video, we're going to talk about estimators of population parameter. So take for example, we are now looking at the distribution of weight of Singaporeans. What we can do is we can go up to every single Singaporean, or 6 to 7 million of them, and we ask them a question, how heavy are you? Mr. Tan, he weighs 72 kg, so we will go to 72 and we'll put one little dot there. And then this goes on for another 6 million times. Eventually, you will form maybe some kind of distribution of Singaporeans' weight. And after collating all of them, you might get a shape that looks like that. Whatever the distribution is, this is clearly not a normal distribution. And this blue color graph here depicts the distribution of Singaporeans' weight. Singaporeans' weight. Let's just call this distribution X. This is clearly not a normal distribution. Whatever distribution it is, that is not so important for now. We're interested in finding the average Singaporean's weight, in other words, the population mean, and we will call this mu. This would represent population mean. However, in real life, this is not a realistic way to find out the actual mean of the population because we can't possibly go up to every one of the Singaporeans and ask them, hey, what's your weight? What's your weight? Add them all up, add all 6 million of them up, and then divide by 6 million. This is clearly not a very efficient way of finding the population mean. So to do this, we would have to estimate it. This is always a huge mystery to find out. And instead of finding this, we would like to estimate it. So we're going to talk about estimators in this video. How do we estimate certain population parameter? Other parameters include variance, like sigma square. Population variance. So let's take a look at what makes an estimator a good one. Now, of course, there are bad estimators and there are good estimator. One of the criteria for an estimator to be labeled good is it has to be unbiased. The other factor in determining whether an estimator is good or not, it would be whether the estimator is efficient. So only if an estimator is both unbiased and efficient, we can say that it is a good estimator for these population parameters, such as mean, variance, and other things like mode, median, and so on. But these are the two most common ones that we are trying to estimate: population mean and population variance. Whether or not an estimator is efficient or not, sadly, is not in your H2 syllabus. You don't have to show whether an estimator is efficient. You don't have to find out whether an estimator is efficient. All we need to know for now is whether or not an estimator is biased or unbiased. So this raised the question of what is the meaning of an biased estimator versus an unbiased estimator. So let's take a look at how do we estimate population mean first. One way to estimate the population mean would be to select, instead of selecting all 6 million of them and asking them for their weight, we're going to select a selected group of 50 people, selected randomly. How they are selected, the selection process will be talked about in another video. So let's select a group of 50%. Maybe I choose this guy, this guy, this guy, this person, this person, this person, this person, and so on. We have 50 of them. Now in this group of 50, what we can do is we can find out the mean of these 50 people. So instead of finding 6 million people, total weight, and dividing by 6 million, all we need to do is select randomly a size of 50 people. This is known as a sample. What happens is we can calculate the average weight within this sample easily because it is just adding up the weight of 50 people and then dividing it by 50. So each and every one of these person will be known as an X, right? So if we were to add up x1 plus x2 all the way until x50, and we divide by 50, this would give us the mean of this sample. So this notation here, tiny x bar, is known as the sample mean. So sample mean, spoiler, it is actually a really good estimator for population mean because of the fact that it is both unbiased and efficient. But of course, let's not talk about efficiency here. Why is it unbiased? And what is the meaning of whether an estimator is biased or not? For example, let's pretend this is the true population mean. Whatever number it is, we don't know. Nobody knows what this number is. We are supposed to estimate it. But for this purpose of this exercise, let's pretend we actually know it. Okay, it is 68 kg. Okay, don't tell anyone. This is the hidden value, the true population mean. Now, if you select a group of 50 and we were to find out the mean of these 50 people, the sample mean can take on many values, right? Sometimes you can get a value of 62.7 kg. So 62.7 kg, maybe it's like here. Sometimes you can happen to choose a heavier set of people and you manage to end up with a number such as sample mean equals to 73 kg. So maybe it's here. Sometimes you might get a sample mean of, let's say, 68.3, which is really close to the true population mean, which we do not know what it is. So maybe it's here. If we were to do this many times, you keep selecting groups of 50 and calculating that group's average weight, you would get something like this. You will get many, many values. Each and every one of these dots, right, represent a particular sample's average. So this particular dot here represents a particular sample's mean. So if you were to do this millions and millions of times, you would get something like that. What did you notice? We noticed that the center of these green colored dots matches up with the true population mean. In other words, the average of all these sample mean matches up with the true population mean. In mathematical notation, this is what we're going to write. The expectation of your sample mean is actually equals to the true population mean. This is what makes a particular estimator unbiased. As long as the average of this estimator, in this case, this estimator here, we're talking about its sample mean, when this estimator's average aligns with the true population parameter, it would make it unbiased. Now let's move on. When we take a sample of 50 people, not only we can find out the mean of the sample, right? We can also find out the variance of the sample. So once again, you have that same group of 50. We can find out these 50 people's variance. In other words, we are finding out the sample variance. We might think that, oh, since we can use sample mean to estimate population mean, it is a good estimator since it's unbiased. Are we able to do the same thing to estimate this particular parameter here, known as population variance? Can we use sample variance to estimate population variance? Let's see what's going to happen. So same thing, these 50 people, we can calculate its variance. So let's say we have the true population variance here. Population variance. And we do not know what this value is, but for the sake of this exercise, we pretend like we know that it is 2.7 kg. Here, we will call this sample variance. Let's denote it as V, for example. So once we go and calculate this V, in this first sample, we calculated V to be 2.3 kg. The sample variance in this group is 2.3 kg. Once again, go back and mark out where 2.3 is. It's a bit to the left. Now we're going to do it again, and this time around we get a particular value such as 2.8 kg. So it's here. Once you continue doing this many, many times, okay, so this is the first sample variance, second sample variance, we do it many, many times. we will get a bunch of dots that look like this. And each of these dots represent a particular sample's sample variance. You notice the difference between this picture and this picture? The center of your sample mean would fall in line with your true population mean, but the center of this sample variance, in other words, the average of your sample variance, is actually slightly to the left of the true population variance. Your sample variance will consistently underestimate your true population variance, which makes it biased. So your expectation of your sample variance is actually lower than your true population variance. So sample variance is actually a biased estimator of your true population variance, which makes it not a good estimator. So how do we refine this? How do we make it unbiased? Very simple. Through lots of algebraic manipulation and proving, you'll find out that the moment we scale this value up by just a little bit, by how much? We scale it by n over n minus 1. This is the magic number. So this is a multiplier value. The moment you attach it to your sample variance, immediately we will make it unbiased. I'm not going to go in depth on how you derive this value, but of course, if you guys are interested, I will create another video and show you the mathematical proof. Why is it this value? You don't really have to know in H2 syllabus. So how do you use it? So for example, just now, our group has 50 people. Our sample size was 50. And we calculated a particular sample variance from this sample. Is it good enough? No, it's not. How do we make it an unbiased estimator? You have to multiply this sample variance that we calculated by 50 over 49. The moment we multiply this, 50 over 49 times sample variance would now be the unbiased estimator of population variance. And it is denoted by S squared. So to sum up, why we need estimator is because population parameters such as population mean and population variance are really difficult to find. We do not have the resources to go up to every individual and ask them for their weight. So what we do is, if we really want to find out what is the average weight of Singaporeans, we will estimate it. What do we use to estimate? We use sample mean to estimate population mean because it is both unbiased and efficient. So how do you know whether an estimator of the parameter is biased or not? Is you go and find out what is the expectation of that particular estimator. If it lines up with the true population parameters, then we say that it is unbiased. As you can see, sample mean here is unbiased because the expectation of sample mean lines up with the true population mean. And below here, is sample variance a good enough estimator for population variance? The answer is sadly no, because it consistently underestimates the true population variance. As you can see here, the average of this estimator is always smaller than the true population variance. We say that sample variance is biased estimator for true population variance. How do you enhance it? How do you make it unbiased? We have to multiply by the magical multiplier n over n minus 1, where n is your sample size. By scaling it up just a bit, we would make it unbiased. This is denoted as S squared, the unbiased estimator of population variance.